We cover a lot of different subfields on my guide to the galaxy because the universe is just way too interesting to stick to a single topic. That being said, of course I love to talk about my subfield, which is planetary dynamics. So today we are going to do a deep dive into a dynamics topic which is called mean motion resonances. But first, I am so thrilled to say that this video is being sponsored by the board game For All Mankind, which incorporates planetary dynamics into the gameplay. How cool is that? It's a strategy resources-based game, and you get new resources by going to different planets of the solar system and Pluto. And the planets move every round. It's for 1 to 4 players, so if you're an introvert like me, you can just play by yourself. But of course, you can also play with friends. Not only is the game and the board beautiful, but it's actually based on real orbits. So as you get farther away from the sun, the period of an orbit increases to the 3/2 power. And so it takes longer and longer for planets to complete an orbit as you get further from the sun, and that is true in this game. Since planets can be anywhere in their orbit, it's really crazy how much the distances change, and you can visualize it beautifully, and of course, you have to take it into account in your strategy. So if this sort of space-based strategy game sounds fun to you, which duh, you can head on over to forallmankindgame.com/Nora and get yourself a copy. Buying this game not only supports the channel, it also supports a small independent media company, and most importantly, you will get an awesome addition to your game night that I genuinely think you will love. So please check this out at the link below, and thank you so much to Bad Cat Media for sponsoring this video. Okay, so mean motion resonances. That's kind of a weird name. Also, isn't it funny how your perspective adapts to what you know? Because mean motion resonance is often abbreviated as MMR. And so when I see that initialization, mean motion resonance is what I think of. Measles, mumps, and rubella who. By the way, we're going to be talking a lot about orbits in this video, so if you're not already familiar with that, you might want to watch this Introduction to Orbits video before continuing. Mean motion is just a property of orbits that's related to the period, that is how long it takes to complete an orbit. It's basically just taking that time and inverting it so that you get an angular speed or frequency, so that would be, 360 degrees per period or 2 pi radians per period. And the reason that it's called mean motion is not because it's insulting you, but because since you're using the period of the whole orbit, it's actually an average of the angular speed of the orbit. Because we know from Kepler's second law that planets move faster in their orbit when they're close to the star and slower when they're farther away. So at any given point in the orbit, they're going to have a different orbital speed than what the average or mean motion is, unless it's a perfectly circular orbit. So that's all we mean by mean motion. Intended. It's just the average orbital speed it takes a planet to complete its orbit. For Earth, for example, it has a sidereal period of 365.256 days, and so if you invert that, that would be 0.9856 degrees per day, or 717 microradians per hour. You can convert to any sort of unit here as long as it's some sort of angle per time. Fun fact, there is a unit for angles called an hour, which is equal to 15 degrees. So you could convert this into 0.0027 hours per hour. And that actually does just equal 1 divided by 365.256 because of the similarity in how we define an hour for angles and for time. Also, do not confuse the use of hours, minutes, seconds to measure angles in astronomy. For example, we usually see this with right ascension, with the use of arc minutes and arc seconds, which are often used to measure astrometry or the position of objects in the sky. So 1 arc minute is 1/60th of a degree, and so they're off by a factor of 15. That is, 1 minute of right ascension is 15 arc minutes. I'm not the one who came up with this, so direct your complaints elsewhere. Okay, we're straying a bit far afield here, but the point is that you should always know what units you're working in. Very important. Okay, that's mean motion. What about resonance? Well, this is the same thing that we mean when we talk about resonance in physics, which is just a phenomenon where the effect of an external force is amplified because it's acting on an object at the same frequency as some frequency that is intrinsic to that object that it's acting upon. And we actually use the term in a similar way colloquially. So if I read a book that I really loved, I might say that book resonated with me because something about that book was very similar to something that I already had inside of me. You could say we were on the same wavelength. But I just mean this in a isn't language cool and how we think about concepts in a sort of way, not in a science is actually telling us our vibes are compatible kind of way. All right, back to the physics. So one of the most common examples that gets talked about when it comes to resonance is the idea of pushing someone in a swing. The motion of the swing is periodic and it has a natural frequency that's associated with just the length of the chain. So if you're standing behind someone and you push them every time they get close to you, you're pushing them at the same frequency that the swing is swinging. You're doing it once per period. And doing that amplifies the effect of your push so that the swing starts to go higher than it would if you were just pushing at random points within its swing. Now a swing has a really obvious natural frequency, but natural frequencies are all over the place. Think of a wine glass. When you tap on it and it releases a note, that note has some frequency, and that is the natural frequency of the wine glass. And then this is how singers can, in theory, break a glass with just their voice. Because if they can sing that exact same note, that's an external force on the glass at the same frequency, so it'll have a larger amplitude of oscillation, and that breaks the glass because glass doesn't bend that well. So it's not actually about how high the singer is singing, it's about how closely they're matching the natural frequency of the glass and how loud they're singing. Back to planets. Now, since planets move in orbits that have periods, hopefully it's not surprising that planets exhibit periodic motion. And so just like with any other resonance, if you apply some external force to a planet in its orbit that is operating on the same frequency as that periodic motion, things can get crazy. That's exactly what's happening in a mean motion resonance, and the natural frequency here is that mean motion, which we already established is a frequency. But it's not just the one planet's mean motion. See, we often talk about the Keplerian orbit of a planet, which is the perfect idealized orbit in which the planet, which is perfectly round, is orbiting a star, which is perfectly round, and there's no other objects anywhere around. But of course we know that there are other objects around, in particular, other planets. And yes, the sun is so much more massive than any planet that its effect really dominates the motion of the planets. But gravity is always acting in between all of the bodies involved, even between the different planets. Consider a still idealized but slightly more complicated scenario where you have two planets orbiting a star. Now, the strength of gravity depends on distance, and not just the distance. It depends on the distance squared. So the strength of gravity falls off really fast as objects get farther apart. So of course, the strongest interaction between the planets happens when they are closest together, which we call being in conjunction. And you can actually think of this interaction sort of just as a little kick that's happening at the moment in time where they are passing by. Let's consider what that would look like for most of the two planet systems that we could come up with. The planets interact at that closest point, and the location of that closest point changes as they orbit. In fact, you can quickly see that these kicks begin to fill the entire orbit. But there are some configurations of two planet systems we could come up with where this point of conjunction is not changing over the entire orbit, and instead it's happening at the same couple points over and over again. And what does that sound like? Yeah, that sounds like pushing a swing. Except here, the swing is the planet, and the thing pushing it is also the planet. It's the both planets, and just like the swing got higher than it otherwise would have because of the resonance, the effect of the gravitational interactions between the planets is much stronger if they are in resonance. So what are the frequencies at which mean motion resonance can happen? Well, it's when the frequencies, or therefore the periods, are integer multiples of one another. That could mean that one planet has an orbit that's twice as long as the other planet, or 3 times as long, or 4 times as long, etc. But that's not all, because it could also mean that one planet has a period that is 3 times 2 times the other planet's period. So if you can find some combination of two integers, m and n, such that m times the period of one planet equals n times the period of the other planet, then you've got yourself the potential for a mean motion resonance. And what we call the order of the resonance is just the difference between those two integers. So a 2-to-1 resonance would be first order, and so would 3-to-2, but a 3-to-1 resonance would be second order, and a 5-to-2 would be third order, etc. And in general, the lower the order, the stronger the resonance. This is often expressed as a period ratio, which is just the longer period divided by the shorter period, which for a mean motion resonance will always be a rational number like 1.5 or 2 or 4 or 2.5. You get the idea. And note, I said that if these two integers exist, then you have the potential for a mean motion resonance, because it's not quite as simple as just calculating the period ratio and calling it a day. So why might planets have this sort of special period ratio and not be in mean motion resonance? Well, for one thing, the orbits are not perfectly Keplerian, right? We know that they're changing over time because the planets are affecting one another. And so their periods are also changing over time. So that period ratio is really only true for a brief point in time, and you might measure it as, say, 2.001, and then you come back a little bit later and it's 2.06. So that 2.001 didn't actually mean that it was in resonance, it just got close for some random point in time. Now that's on a very small scale of the periods changing very slightly over time. But periods can also change on this macro scale because planets can migrate throughout the system. And in that case, they might just be sort of passing through this period ratio, and so they don't actually stick around to stay in mean motion resonance. Basically, they don't get enough of those evenly spaced kicks to overcome whatever else is happening to their orbit. And remember, orbits are 3-dimensional, so the planets might not even be orbiting within the same plane at all. And as you get these really high mutual inclinations, then things can get weird. But this sort of thing happens in the other direction as well, and that you might measure a period ratio that is not actually exactly this integer multiple, and yet the planets are still in mean motion resonance. Basically, every mean motion resonance has some sort of width in period ratio space, and the details of which depend on the order of the resonance and the eccentricity and inclination of the orbit. In fact, this was the subject of one of my PhD papers. So for second order resonances, as the eccentricity of the planets increases, the width of the resonance gets a lot wider. So that is, planets can have a period ratio that's farther away from like that exact resonance and still be in resonance if they have a high eccentricity. But remember, I said those period ratios are actually changing over time by pretty small amounts, but if you average over time, if they're in resonance, those period ratios will actually average to really, really close to that exact number of the resonance. That means that if you looked at a bunch of different planet pairs and you averaged their period ratio over time, the more eccentric those planets tended to be, the higher and sharper the peak would be right at the exact resonant value. I'm not gonna lie, I reread that paper when I was writing the script for this video and I cried a little bit because I already forgot so much of what I did, and it's only been a couple years, but I guess that's what I get for leaving academia. But now I get to share what I do remember with you, and Dan, I'm sorry if I'm getting anything wrong. All right, so if measuring the period ratio isn't actually enough to tell you whether or not a pair of planets is in mean motion resonance, how do you tell? What does it mean for a planet pair to be in resonance versus near resonance? So the long answer here involves Hamiltonians, and I know this is a deep dive video, but it's not that deep of a dive. But in general, the takeaway is that you can look at various combinations of angles between the two planets and then look at how those values change over time. Remember, mean motion resonance involves two planets, and those planets are orbiting something, and that is three bodies, aka the three body problem, and so we know that a perfect analytical solution literally does not exist. So we have to use approximations and models to investigate the behavior of these systems. This is typically done using those angles that I just mentioned, which are called the resonant arguments or critical angles. And basically they're just calculating the angle of conjunction. That is that point where the planets are closest together. For a first order eccentricity type resonance, this is how you calculate those two resonant arguments. And the angles that are being used here in this calculation are the mean longitudes of the inner and outer planet and their longitudes of pericenter. So if you calculate the critical angle over time, it's generally going to do one of two things. It's either going to circulate or it's going to librate. If it's circulating, that means that it's going through all of the angles. So if you think of the angles of a circle, circulating just means that it's spinning through all of the possible angles over time. But if it's librating, that means it will only experience a slice of possible angles. And so it'll basically just bounce back and forth within that slice, and it's not going to go all the way around the circle. And if one or both of the critical angles is librating, then the planets are in mean motion resonance. For these resonant planets, as that critical angle moves away from the resonance, the interactions between the planets basically act to move it back towards the resonance. And that is how they lock their relative orbits in, so to speak. All right, so that's what it means for planets to be in mean motion resonant. But what does it mean? What does it do? Well, just like with any resonance, it can do a lot because you're getting amplified effects, so you can have really big implications. Consider, for example, a planet migrating through its protoplanetary disk, and then bam, it reaches a location where it's resonant with another planet. The strength of that resonance can stop that planet in its tracks and halt its migration, which has huge implications for what the planetary system is going to look like once the dust settles, so to speak. In fact, in general, given that it's hugely unlikely for two planets to just happen to have the exact right periods to be in resonance, planetary migration is very related to mean motion resonances. This is really cool because it can tell us things about the history of a planetary system that we weren't around to see, like in our own solar system. Consider Neptune, the furthest planet from the sun. Neptune is in a lot of mean motion resonances, not with the other planets. None of the planets of the solar system are actually in mean motion resonance with one another at the current point in time. But Neptune is in a lot of resonances with small bodies located in the outer solar system in the Kuiper belt, the largest group of which is called the Plutinos. As you may guess from the name, Pluto is in fact a Plutino. In fact, it's the largest Plutino, but it's not the only one. There are hundreds of them, way more than would be expected by random chance. The Plutinos are all in 3-to-2 mean motion resonance with Neptune. That means they make 3 orbits for every 2 orbits of Neptune. No, that means they make 2 orbits for every 3 orbits of Neptune. The existence of this pileup of objects in the 3-to-2 resonance implies that in the past, Neptune migrated outwards and basically scooped them all up into this resonance. And while Plutinos are the most numerous, they are far from the only group of Kuiper belt objects that are in resonance with Neptune, including Tutinos in the 2-to-1 resonance and dozens more in the 4-to-3, 5-to-3, 5-to-2 resonances, many, many more resonances, including one confirmed example of a 16th order 21-to-5 resonance, which is crazy. And Pluto's 3-to-2 resonance with Neptune isn't just evidence of the history of the formation of the solar system, it's why Pluto can even exist where it exists at all. See, Pluto has a highly eccentric orbit of 0.25, so that means that its closest point to the sun is just under 30 AU, and its furthest point is almost 50 AU, while Neptune has a close to constant 30 AU distance. That means that although Pluto's orbit has a larger semi-major axis, it actually gets closer to the Sun than Neptune does, and that is what we call orbit crossing. And that is generally real bad news, because orbit crossing usually leads to instability on really short timescales. Think back to what we said about how the closest point of approach between non-resonant planets tends to vary throughout the entire orbit. Well, if you have crossing orbits, then it's only a matter of time until the two planets get close enough that they either collide or one gets ejected. Unless you have a mean motion resonance, which is making those closest point of approach happen only at certain points, not throughout the entire orbit, and then the two objects can happily exist because they never actually get too close together. And so the 3-to-2 resonance with Neptune is basically why Pluto hasn't been yeeted. But while mean motion resonances can be really protective, like Pluto and Neptune, they can also be really destructive. See, being in mean motion resonance is generally pretty stable. The critical angle is librating over time, the planets are happily doing their dance, it's all going great. But as the planets get closer to being in mean motion resonance without being in resonance, things get chaotic, literally. Remember, the resonance is increasing the effects of the interactions between the planets, and the larger the effects are between the planets, the harder it is for them to coexist in a stable configuration. Consider a one-to-one resonance, which is a very special type of resonance called a co-orbital resonance, where the two bodies basically have the same period. In general, as you can probably imagine, this state of things does not exist for a very long time because the larger object is just going to throw its weight around and clear its orbit, and the smaller object is going to go elsewhere. But then again, we know that the Trojan asteroids exist at the same period as Jupiter, and Jupiter has more weight to throw around than anyone, so how does that happen? Resonance. The Trojan asteroids are in resonance, and so their orbits are protected, but all of the other objects that weren't in resonance but just near resonance are gone. Another example is the asteroid belt. So the asteroid belt is a donut-like structure of asteroids in between Mars and Jupiter, filled with asteroids ranging in size from little bitty little rocks up to a freaking dwarf planet, which is Ceres. Oh, and this is one of my favorite space facts, but the asteroid belt, even though it has millions of asteroids that are a kilometer in size or larger, and millions more that are smaller than that, plus, like I said, Ceres, the dwarf planet, if you added up all of that mass, it's still less than 3% the mass of our moon. Alright, so if you look at a distribution of all the orbits of those asteroids in the asteroid belt, something is immediately obvious. There are some huge gaps in there, and those are called the Kirkwood gaps. If you compare the location of those gaps with the orbit of Jupiter, it'll become immediately obvious that they're all located near lower order mean motion resonances with Jupiter, like this huge gap at the 3-to-1 mean motion resonance. That's not a coincidence, but it's also not the whole story. See, the MMR with Jupiter isn't causing the instability by itself, but it is setting the stage for instability when combined with other effects. In this case, secular resonances, which I'm sorry, that's a whole other kind of worms we could not possibly get to today, so you'll just have to accept that they exist. Really, the solar system is just an incredibly complex dynamical system. Any explanation is some sort of approximation. Speaking of complex dynamics, what if you have an object that's in mean motion resonance with more than one other object? Is that even possible? Well, I'm glad you asked, because yes it is. This is called a resonant chain, and they are very cool if you ask me. And get this, not only can you have a situation where A is in mean motion resonance with B and B is in mean motion resonance with C, you can actually have a larger 3-body resonance where A, B, and C are all in a single resonance with one another, which is just like the perfect celestial dance. And this isn't theoretical. We actually know of 3-body resonances that exist, like the Galilean moons of Jupiter and the exoplanet system Gliese 786. We even know of a 4-body resonance in the exoplanet system Kepler 223. That means that there is a critical angle that you can calculate using all 4 of the planet's orbital properties, and that critical angle librates over time in simulations based on observations from Kepler. Fun fact, this was actually discovered by one of my academic siblings in the sense that we had the same PhD advisor. And if you're just considering chains of individual resonances, there's a 7-planet resonant chain in the TRAPPIST-1 system, and that includes 3-body resonances. Now, these examples notwithstanding, it's actually relatively rare to find exoplanet systems in resonant chains. And that in and of itself is interesting. Not just the presence of a mean motion resonance, but the lack of a mean motion resonance. Because remember, I said that these mean motion resonances can stop the migration of a planet in its protoplanetary disk. And in fact, planets are basically always migrating in their protoplanetary disk. And so you would expect that as these resonances catch the planets up, then you would form systems in resonant chains. And that's not what we see. The fact that we don't see these resonant chains very much indicates that there is something else that's happening in the process of forming a planetary system that's disrupting the initial resonant chains. One 2017 study found that 95% of initial resonant chains have to be broken to be consistent with our observations. And understanding exactly why and how those resonant chains are getting broken is a very active area of research. So, mean-motion resonances are not just a fun and challenging mathematical problem. They're not even just a beautiful dance of celestial objects or a chaotic flinging of the same. They're a probe of how planetary systems form in general and the history and evolution of our own solar system. Doesn't get much cooler than that. Thanks so much for watching, and do not forget to follow the link and go get yourself a copy of this board game for all mankind. Thank you! Bye!